Greetings, everybody, and happy Monday. Um, you'll see one thing that's different here. I am hoping that having this earpiece connected into my laptop will actually deal with some of the volume issues that we've had previously. I've been noticing as I've tested this that we have some connectivity issues, so every once in a while it may go blank. Every once in a while also there's a syncing issue where my mouth's going like this and then you actually hear the volume. So hopefully it won't seem like a bad foreign film. Um, we'll have to see. Just to give you an overview for um, this week's fairly normal. One of the only things that's kind of weird is that Wednesday is a service day, from what I remember, which means that we're going to have a shorter time period, which means we have a shorter lecture. One of the issues with having a shorter lecture is that I think you have on Wednesday you've got homework due today, and I'll talk about that in a second. Then you've got homework due on Wednesday, and homework due on Wednesday is just 4 optimization problems. I know I say just 4. Those optimization problems can be long sometimes. I don't think I'll have time to actually do some of the homework in the lecture itself. So what I'm going to do is record a separate lecture where I'm going to run through 2 of those problems myself. I'll upload that to RenWeb. And if you've never seen, all of these lectures are actually on RenWeb and they're on YouTube. So if you haven't gone there and you want to have access to this, go to the web items. There's a resources tab on RenWeb and there's web items. And there's the websites on YouTube where these things are linked are right on there. So feel free to go there and explore. But this week we've got homework due today, homework due on Wednesday, and then a quiz on Thursday, kind of like normal. Next week is going to also be a normal week. There won't even be a service day. So next week will be normal Monday, Wednesday, Thursday. You can be praying for me. I am not in class, obviously, but we actually have a lot of our international leaders here in the Grand Rapids area from many different countries around the world, and we're doing some strategic planning for reaching deaf communities in various parts of the world over the next 2 weeks. So you guys can be praying for me in that. That's obviously another reason that I'm not here. But today my plan is to go through 2 of the optimization problems that you'll see on the homework. I know that you had 3 graphing problems and then 5 optimization problems. 3 of those optimization problems shouldn't have been too bad. You might have some questions on the graphing problems. Ms. Barabo has the solutions. So assuming that this video doesn't go too long, you guys might have some extra time to work and ask questions on any of the homework problems that you have for today. If you're not able to get the homework done for today, these graphing problems are long, the optimization problems are long. I understand that. You can take until Wednesday. We'll probably post these solutions up there just so you can see them and you can try to work through them. And then I'm willing to bump those 4 problems on Wednesday to Thursday if you need to do that. So there's a little bit of flexibility there. Let me go ahead and run through 2 of the optimization problems that are on your homework. And then basically the rest of the time I'm going to do a few more optimization problems, and there's a few things that I want to actually show you that are pretty cool related to optimization and related to creation and how God has created this world pretty fearfully and wonderfully. So we'll talk about that in just a few minutes here. So I want to look at just at least the setup for problems 18 and 23 from the optimization homework. Okay, so we're going to look at section 3.7, starting with number 18. So here, a rancher has 200 feet of fencing, and that person is creating 2 adjacent rectangular corrals. So we're basically fencing off an area where these 2 lengths are the same, and then this length may be different, and altogether 200, I think it said 200 feet of fencing. And the question is, how do we maximize the area? So again, the first thing that you should write down, well, besides your picture, you should have a picture up on your paper. The first thing that you should write down is that you're trying what are you trying to maximize or minimize? We want to maximize area A. And obviously the formula, well, obviously, and then I write it wrong. Obviously, the area formula is going to be length, which is 2x, times the width, which is y. So that's our area formula that we want to maximize. The problem is that we have two variables there, and we don't want two variables. We want one variable. So we need to use this information over here to get rid of one of those variables. So the total amount of fencing that we have to use here, we have 3 copies of y and 4 copies of x. So 4x plus 3y is 200. All right. And so now I need to solve for one of these. I'm just going to solve for y. So 3y is 200 minus 4x, and then I'll divide by 3. So I've got 200 over 3 minus 4/3 x. That's my y. And then I'm going to take that and substitute that back in here for y. So my area is 2x times this thing. 200 over 3 minus 4/3 x. So in other words, it's 400 over 3x minus 8/3 x squared. That's my area if I multiply this out. I don't like the product rule, so we're going to try that so this is your formula now. You're just going to differentiate and then set that equal to 0 and solve, and then just check and make sure that wherever you're at, we want to maximize, so you should be seeing positive slope over here and a negative slope over there, and then that will maximize your area. Okay? So that is number 18. That at least gives you the setup there for number 18. So let's take a look at the, pardon me. Let's take a look at the setup for number 23. This is the other one I wanted to go over. So a Norman window is constructed by joining a semicircle on the top of an ordinary rectangular window. Okay, so in other words, we have a rectangular window here, and then that part is a semicircle. So that radius is the same. So we need to find the dimensions of the Norman window that maximizes the area if the perimeter is 16 feet. Okay. So again, what we're going to write down here after drawing a picture and crying, if we need to do that, is what are we trying to do? So again here, we want to maximize the area A. That kind of makes sense because if you have a window, you're going to want to get the most light normally. So what I'm actually going to do here, you don't have to do it this way, but I'm actually going to call half of this thing x, because then that's going to give me a radius, and it's nice to work with a radius rather than a diameter. So I've got an x here and x here. The height here may be different. You can call it y or h. This is x, this is x. So the area here is going to be the area of the rectangle, which is 2xy. That's the rectangle. Plus the area of half of this circle. So if the area of the circle is pi r squared, this is my radius. So this would normally be pi x squared, but I want half of that because this is a semicircle. Okay. So I've got rectangle and semicircle. Now notice again I have two variables, x and y. Now I only have one copy of y, so it makes sense for me to try to solve for y and get rid of y. And again, the way that I do that is use this extra information that I have over here. So my perimeter is 16 feet. I've got perimeter here, here, here. I'm going to have to figure out how long this is. Well, the circumference of a circle is 2 pi r. My r here is x. That's a whole circle. This is half a circle. So the circumference there is going to be half of that, which is going to be pi x. So my perimeter, which is fixed, it's 16, is going to be 2 copies of x, this part, 2 copies of y, and then that half circle there, pi x. Okay. And again, it's going to be easy to solve for y and just stick that in here and get everything in terms of x. So let's throw everything with x on the other side. So I'm going to subtract the 2x and the pi x over. And then if I solve for y, y equals 8 minus x minus pi over 2x. And so that is going to go right up into my y formula here. So my area now is 2x times this thing right here plus pi over 2x squared. So if you stick that in and kind of multiply that out, then you'll have a formula for the area, and that's something that, again, you can differentiate and then check and make sure that what you get is actually your maximum. Okay? So that should give you the setup for those two problems. Hopefully that will help you out here. Okay? Okay. So what I'm going to do for the rest of the time here, I'm probably only going to go, well, we'll see, maybe about another 35, 40 minutes. Then you'll have hopefully some time to work on homework. What I'm going to do is in part some modified versions of other problems in the book, in part some kind of, I'll show you a few other types of problems. And like I said, we're going to talk about how there's some pretty crazy stuff that you end up finding in nature, the way that God's created this world as a result of some of the mathematics that we get to see. It's going to be pretty cool. So I'm going to do, this is not a homework problem, but this is another example one that I want to do. I want to do a modified version of 41. Now 41, if you have your book there, it says the sum of the perimeters of a equilateral triangle and a square is 10. Find the dimensions of the triangle and the square that produce a minimum total area. I want a minimum area. Now I'm going to modify this problem. I actually want to work with a square and a circle. Okay, so here's the idea of the problem. We've got some wire. In fact, we have 10 something. It doesn't actually say. So let's just say 10 feet of wire. And I want to construct two things. I want to make a square, and I want to make a circle with the wire. So I'm going to take my wire, I'm going to chop it, and with this part, I'm going to bend it in these 4 places and construct a square, and then with this part, I'm just going to wrap it around and make a circle. And the idea is I want this area plus this area to be a minimum. Okay, we're going to have to make sure that we're super careful. So I want my total area here. I want to minimize, erase this here. We'll go ahead and do this too. want to minimize my total area. So let's write that here. Minimize total area. Okay. So what I need to do first, we've got to put a variable somewhere. So what I'm going to do is I'm going to call one of these sides of the square x. So this is x, x, and x. So in other words, x, 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 x. In total, this part of the wire is 4x. The whole length of the wire is 10. So that makes this part over here what? How long is that? That's going to be 10 minus 4x. So in other words, around the outside here is 10 minus 4x. If I choose one of these sides to be x, then around the outside is 10 minus 4x. Okay, so the total area that I want is going to be the area of the square plus the area of the circle. Now the area of the square is going to be pretty easy here, the way that I've labeled it. It's going to be x squared, x times x. Now the area of the circle, well, if this is here, and we'll figure out what the radius is, then the area of the circle is going to be pi r squared. So our now is going to be to get that area. I have two variables in r, but they're related in some way. They're related by this being the circumference and this being the radius. So we're going to have to probably eliminate one of these. I'm guessing r, and then we'll put that in and use our calculus to figure out how we're going to get the minimum area. Okay, so let's see. So the circumference is 2 pi times the radius, and the circumference is 10 minus 4x. We already know that. So that lets us solve for r. So if I divide by 2 pi, r is 10 minus 4x over 2 pi. So let's put that into our area formula here. So we've got x squared plus pi times r is 10 minus 4x all over 2 pi squared. Okay? All right. Now, we just have x's in there, but in order to actually differentiate, clean this up a little bit because this is kind of messy. All right, I've got a pi in front. I've got 10 minus 4x that's going to be squared. And on the bottom, I've got 2 pi that's also going to be squared. So I've got 4 pi squared. So let's cancel one of those pi's at least. And we've got 1 over 4 sitting there. And now let's multiply out 10 minus 4x times 10 minus 4x so that we can get this so that doing the differentiation is going to be a lot easier that way. Okay, so if we FOIL first, it's going to be 100. The outer is minus 40x, and the inner is minus 40x. So we get in total minus 80x, and then plus, if we negative 4x times negative 4x is going to give us plus 16x squared. So what we see is my area is 100 over 4 pi minus 80 over 4 pi x plus 16 over 4 pi x squared. And if we simplify that just a little bit more before we differentiate, we get 25 over pi here, 20 over pi x, and 4 over pi x squared. Okay. So I know this looks ugly. That's okay. So now we have our function with just x, so let's differentiate. We've got it in a nice format now. So the differentiation should be pretty easy. If we differentiate x squared, we get 2x. This constant term goes away. Constant times x, the derivative of x is just 1, so we're just going to get that constant. Plus 4 over pi, and again, the derivative of x squared is 2x. So what we end up getting is 2x, let me rearrange this a little bit, plus x minus 20 over pi. Okay. So let's set that equal to 0. And we're going to try to solve that. So constant term over 2x plus 8 over pi x equals 20. Now we can factor an x out. 2 plus 8 over pi equals 20 over pi. And then we can divide this over. So now x is 20 over pi all over 2 plus 8 over pi. Now, that's having fractions and fractions is awful. So again, let's multiply through the top and bottom by pi just so we get something a little cleaner. 20 over 2 pi plus 8. Okay. Let's see what happens. We've got 20 over 2 pi plus 8. Just so you kind of have an idea of this, 2 pi is about 3. So this is about 6 plus 8 is about 14. 20 over 14 is about, it's 1 point something, like 1.3. So the idea is this would be 1.3, 1.3, 1.3, 1.3, about 5.2 or something like that, and then the rest would be used for the circle. Now the question is this a maximum? Is it a minimum? What are we looking at here? Because that's where the derivative is 0. So if we were to plug in, let's plug in something way on this side. Let's plug in, for instance, x equals 0. Then what we would get, if we plugged in x equals 0 in this derivative, then we would get something that's negative. And then if we plug in something positive, like let's say 2, we're going to get, we should get something positive here. So in other words, we're decreasing and then we're increasing. So this does in fact give us a minimum area that we're looking for here. Okay? So that amount right there, whatever that is, again, it's going to be like 1.3. That's how much we use in the square, and then the rest for the circle in order to minimize the area between both of those that we have there. All right? Okay, make sense? I know the numbers come out, they're not beautiful, but that's kind of how real life works. Okay. All right, we're going to do a couple more, one more at least in detail. Then I'm going to talk through 3 other ones. We're not actually going to do them, but I want to talk through them, okay? All right, so this is not in your book, but this is kind of, this example, when I first saw this, I was like, whoa, this is a really, really cool application of calculus, okay? So let's suppose you're standing on the beach. Okay, so this part is beach. And then this out here is And you also have your dog on the beach. How many of you guys are dog people? This my dog is looking like a duck. My poor dog. At least he has a tail. Okay. Now you have a stick, and what you're going to do is you're going to throw the stick into the water. Okay, and the stick lands. Let's say this is 40 feet out that way, and let's say that it's 4 feet out this way. Okay, so you throw the stick, it heads out this direction and lands in the water. Now let's suppose that your dog can run 8 feet per second on the land and swim 4 feet per second in the water. Okay. Now your dog, the dog may not think through this, but your dog actually has a lot of different options that they can take in terms of chasing that stick. If your dog really hated the water, then what it would do is it would run down here all the way and then take kind of the minimum distance that it has to take to get to that stick up there. Okay, that's one option. Another option, if your dog loved the water, it could just the water and swim all the way directly to the spot. Okay, kind of a middle of the road possibility would be that your dog runs down the beach for a little while and then ends up swimming the rest of the okay, because running and then swimming is probably longer than just swimming. So the question is, what path should your dog take that will minimize the time, that will get your dog there the fastest? What will minimize the time? So let's try this. We want to minimize the time. Okay. And so we're going to call that the total time is going to be t. And what that's going to be is the time going this route and then the time going up here. All right. Now, distance over time, if I started to write DDT because I've got derivatives on the brain. Distance over time is my speed, my velocity. So if I were to switch these two here, my time is distance over velocity. If I want my time, I need to find my distance and then divide by velocity. So in other words, my total time is the distance on the beach divided by the velocity on the beach. That's my time on the beach, plus the distance in the water divided by the velocity in the water, and that's going to give me my time in the water. Okay, so I got my time on the beach plus my time on the water. So now we know the velocities on the beach and on the water. That I've told you already. Okay. So now what we're going to do is we're going to label some distances here so that we can get this all in terms of one variable. So I'm going to call this distance right here x. And so then if this is x and this is 4, my Pythagorean theorem would tell me that x squared plus 4 squared is this thing squared. So this thing is the square root of x squared plus 4 squared. That distance right there. Okay. So in terms of my time, my distance in the water is the square root of x squared plus 4 squared is 16. And my velocity in the water is 4. Okay. Now this overall distance here was 40, so that makes this distance right here. So that's my distance divided by my velocity on the beach. So that is my time. And now I simply want to minimize it. Okay, let's clean it up just a smidge here. 40 over 8 is 5. So I've got 5 minus 1/8 x, and then I've got a fourth of this thing. That'll just make this a little bit easier when I do this calculation, okay? So now let's minimize this time. So we're first going to differentiate. All right. And so the derivative of 5 is 0. The derivative of 1/8 x is just going to give me minus 1/8. Then I leave that fourth alone, and then I've got this thing to the 1/2, so I'm going to take 1/2, that quantity, to the negative 1/2, and then by the chain rule, I need to multiply the derivative of what's inside. So that one's more complicated. Okay. Okay, let's cancel a 1/2 and a 2, and let's rewrite this a little bit. So I've got an x on the top and 4 square root of x squared plus 16 on the bottom. Okay. So I want to find out, where does that derivative equal 0? So let's put the 1/8 on the other side. And then let's multiply this part over to the top here. So x equals, I guess we'll cross multiply. So let's put the 8 over here and the 4. So we've got 8x on this side and 4 square root x squared plus 16. Since we've got the square root, let's go ahead and square both sides so we can clean this up a little bit. So we've got 64x squared equals, if I square 4, I get 16 x squared plus 16. So I've got 64x squared equals 16x squared plus 16 times 16, I think that's 256. So if we subtract 16x now, we get 48x's left. And so x squared is 256 over 48. Let's go ahead and calculate. All right, 256 divided by 48, so I get 5.3. That's x squared. And then if I take the square root of that, x is about 2.3 feet. Okay, so what that means, well, let's check and make sure it's a minimum first. So 2.3. All right, so if x were, let's just say x were 0, in other words, the dog ran all the way here and then went up, the derivative there, this would go away. The derivative would just be negative 1/8. So the derivative is negative there. And if x is a big number, then this number is going to end up being bigger than this. We're going to get a positive number here. Okay, so truly, this ends up giving me a minimum time. So what that means, what we figured out is if your dog runs 8 miles an hour on the beach and 4 miles an hour, 8 feet per second on the beach and 4 feet per second in the water, then your dog's going to run all the way up until it's 2.3 feet away from this edge right here, and then it's going to go directly out into the water. Now, here's the crazy part. This is the part that I was like, what in the world is going on here? What actually ends up being true is that your dog takes that route. Your dog, if you did this in real life, and if these numbers actually, your dog would run down the beach and then shoot out into the water at exactly that point. So in other words, your dog knows calculus. Isn't that crazy? Your dog knows exactly the place to jump into the water and head straight for that stick that's going to give it a minimum time. Now, your dog actually doesn't know calculus, But what's amazing is that God's created your dog so that it somehow goes after the minimum, the path that's gonna get it to that stick in the minimum amount of time. Isn't that crazy? That's amazing. And if you change these numbers, this place changes, but then if your dog has different ratio of how fast it can run on the beach versus the water, where it goes into the water also changes. Amazing. God's created things in such an amazing way. Let me show you another example here. We're not actually going to go through all the kind of nitty-gritty details like we did in this, but this example actually comes from beehives. So as you are aware, bees make their hives with these sort of hexagonal honeycombs. Okay, so if you're looking at the front of the hive, it looks like, there's a big sheet of honeycombs like that. But if you were actually slice it and kind of slice it like this and kind of turn it so it's sideways, what you would see is that these honeycombs, obviously they're three-dimensional. Okay. And when you get to the back of the honeycomb actually comes completely to a point. So it's not flat on the back in the same way that it's flat in the front. It's actually, when it's made, it comes to a point. And one question that we can ask is, like, based on when so these are flat right here, and then this comes to a point. So you can imagine you've got the honeycomb, honey's going in here, and it all comes to a point. You can imagine that there's a specific distance or a specific angle that's going to minimize the amount of material that's required to make this end of the honeycomb. So in other words, if I were to extend this web, obviously that's going to use a lot of material. If it was perfectly flat, that might use a fair amount of material, but there should be some angle here or some amount of material, some distance, that minimizes the amount of material and the amount of energy that bee has to expend to create that honeycomb. Now what's crazy is if you calculate that, if you go through some of the calculation, you'll actually find that the bee uses the minimum angle. Or in other words, it uses that minimum distance that it needs. It conserves energy the best. It does its best. And I look at that and I think, wow, creation is we are fearfully and wonderfully made. And this creation that we have around us, God has instilled within it. These bees aren't thinking this way. They're not doing calculus, but somehow they're using the minimum angle, the minimum construction that they need in order to use the minimum energy. That's amazing. It shows that we have an amazing God who's created everything. One more example that I want to show you here. Okay. So it's actually kind of related to the dog example. So let's suppose that you had a flashlight. Okay, and you were shining the flashlight into the water. Okay, and there's some diver who's down here who's actually looking up. Let's give that person a blue eye. Okay? All right, so they're looking up at the flashlight. I don't know if you know this. I don't know if you've ever seen this before, but light, when it enters the water, it bends. Okay? So when light comes and then hits the water, it actually doesn't keep going at the same angle that it came in at. It actually changes its angle. Okay, it bends. So whereas this angle might be, in math, we tend to use the Greek letter theta to represent angles. So this might be theta 1, which is just one angle, and then it's out at a different angle, and that has to do with how the velocity of the of light in water. The velocity of light in air is actually different than the velocity of light in water. Light moves more quickly through air than it does water. Water is, you kind of think of it as water is thicker than air. So the question is, if light in air has one particular velocity and light in water has another particular velocity, how are these angles related? Again, so the time it takes for the light to go from here to my eye down there is a minimum. Okay, because the light, for instance, could go over here, down, and then go way over here and hit your eye. Now that's kind of weird. We don't really think of light doing that. Light could try to travel all the way through, or it could spend more time in the air and then less time in the water. Notice if it went straight on, it would kind of be in the water a little longer and in the air a little less. So if it's faster in the air than in the water, it's probably going to want to go longer in the air and then shoot down a little faster in the water. And it turns out there's something called Snell's law, and it comes from optimizing the time, from trying to make time for the light to get from the flashlight to someone's eye. And the way that the law works is it says that the sine of this angle over the first velocity equals the sine of the second angle over the second velocity. Okay. Okay. Now, you don't need to know Snell's law, but here's the crazy part, is that light actually takes this path, just like your dog does. Light takes the path that minimizes the time to get from one place to another. So in other words, if the flashlight's here and your eye's here and it's going through water, light doesn't go straight and spend a lot of time in the water. It goes over and then shoots at, minimizes the amount of time that the light is actually traveling, according to this law. So it's crazy. Again, God created these things in the world that work optimally, that work the best, and He's created that inside of them. Obviously, light waves aren't sitting in going, what is the minimum time that it's going to take me to get to the person's eye? Well, what's my velocity in air, and what's my velocity? It doesn't do any of that. It just goes, but it goes at exactly the right angle according to its velocities to get to the person's eye the fastest. It's amazing. There's one problem. I'm going to kind of conclude this now. There's one problem. Number 56. I think I assigned number 64 as a bonus problem. 64 is a fairly intricate bonus problem. It's kind of hard. You're welcome to try, sorry, number 64 is our bonus problem. You're also welcome to try instead number 56, or if you want to do both, that's fine. 56 is kind of an interesting problem. You've got a circle, and the diameter is, I think, the radius is 12 feet, or 12 inches. It'd be a big circle if it was 12 feet. 12 inches, so 1 foot. And then you're going to cut out a piece here of a certain angle. So you're going to cut this part out So it looks a little bit like a Pac-Man. And then connect the two ends together. You end up with a cone. Okay. Now you can imagine taking that cone and actually, putting it upright. All right, so flipping it up and using it like a snow cone. So if I were a snow cone company maker and I was taking paper and cutting this out and then making a snow cone, I want to get the biggest volume possible in that cone. And the question is, how big of an angle do I cut here so that I get the biggest volume? I want to maximize the volume of my cone here. Now my volume is 1/3 the base, pi times radius squared, times the height. Now the radius is not 12. This is where you have to be a little bit careful. Okay, this is 12 right here. Like when you connect these two, that slanted part is actually 12 inches. It's 1 foot. So this is the radius right here, and this is the height. Now the way that you do this problem, if you wanted to do this as a bonus problem, you have to think about the fact that the circumference would normally be 2 pi r, but in this case, in other words, it's the full angle, 2 pi, times the radius. But we don't have the full angle here. The angle that we have is 2 pi minus theta. So the amount around here is not 2 pi times 12. It's 2 pi minus theta times 12. So that is the circumference here, 2 pi minus theta times 12. Okay, so then to get this radius, 2 pi times that radius is this circumference now. So in other words, the radius there is 2 pi minus theta over 2 pi times 12. So that will give you the radius. Once you have the radius, you can get the height using Pythagorean theorem and plug those in here and minimize. Now you actually end up getting a really nice clean answer here, which is really interesting. But if you want to try that, you're welcome to do that. Okay? So you're welcome to spend the rest of the time that you have here. You can take a break if you want to for a couple minutes. Spend the rest of the time working on the rest of your curve sketching problems and the optimization problems due today, or the 4 problems that are due on Wednesday and or the bonus problems. Isn't God awesome? It's crazy how He's created nature this way, and He's given us the tools to be able to understand and see just at least a glimpse of the amazing ways that He's created this world. I'll catch you guys on Wednesday. Have an awesome rest of the day.